Screen is sharing. Hmm, that's it. Good morning. Good afternoon, actually. Okay, let's start with chapter 2. Chapter 2, I have gone through it a little bit outside the streaming, so which means I'll be skipping some parts, but you should probably go through all of it. So, the key concept in MLR is operation, and in this uh, chapter, we are looking at how to define an operation, um, what it contains. Yeah, opaque API, yeah, that we know. Defining a Thai dialect, could define it like this in C++, but instead we do it declaratively, which is easier using TableGen. I don't know much about TableGen, but it looks like some specification language, and yeah, you can use um, that to generate all the C++ code. Oh, sorry. Okay, yes, defining a Thai dialect. Yeah. After the dialect has been defined, it can now be loaded into an MLIR context. Mm-hmm. Mm. Oh, you do this. You need to load it on the dialect, and then by default, MLIR context loads only built-in dialect, which provides few core components, meaning other dialects such as Thai must be explicitly loaded. Okay. Defining Thai operations. Thai operations. Oh yeah. Um, Operation takes zero operands, hidden element attribute named value to represent the const value. Mm-hmm. Okay. This is the result. This is the name of the op. This is where we specify. Brackets are where we specify the inputs, isn't it? Yeah. So const doesn't take any input, is it? This is missing. Mm-hmm. Then they start with angular bracket. Let's see here. Percentage sensor. A list of zero or more input operands or arguments which are SSA values defined by other operations are referring to block arguments. Mm, okay. And a dictionary of zero or more attributes which are special operands that are always constant. We define a Boolean attribute named in place that has a const value of true. Okay. And this particular thing, this refers to a type of operation in the functional form, spelling the types of arguments in parentheses, okay, and the type of return value afterwards. Okay, from this to this and the location. What is this? Zero or more input operands are arguments which are SSA values defined by other operations are referring to the block arguments. Mm, Interesting. Let's find out. This is what I thought is like input arguments, but yeah, they say it a little bit more than just saying their input arguments. They could be from other operation results, or it could be so in this case there are no other operation rules, but so operation takes zero operands. Hmm. This operation takes zero operands, a dense element attribute called value to represent const value, and returns a single result of rank tensor type. Dense element of type tensor 2 by 3 by whatever, and returns from, it doesn't take anything but return that. Oh, okay. An operation class inherits from the CRTP, curiously recurring template pattern, MLIT class, which also takes some optional traits to customize its behavior. The traits are a mechanism with which we can inject additional behavior into operations, such as additional accessors, verification, and more. Let's look at below definition for const operation that we have described below. Const operation inherits MLR op with MLR const MLR op is a curiously, what is this weird thingy? Curiously recurring template pattern. Curiously recurring is a idiom in C++ in which class X derives from class template instantiation using X itself as a template argument. More generally, it can be F-bound polymorphism. Oh, this technique is formalized as this. Some of the earlier C++ template code as well as code to the multi-paradigm language LIDA. Upside down inheritance due to the way it is. It allows class hierarchies to be extended by substituting different base classes. Okay. Curiously, CRTP, TF, CR, uh, TP, CRTP is somewhat like this. Template class type, it takes type T, and then class base. Class derived is from this. Um, ah, okay. Most use cases are static polymer figures prominent in C++ implementation of data context and interaction paradigm. Which is the fact that member function bodies definitions are not instantiated until long after its their declaration will use members of the derived class within its own member functions via the use of cast. For example, there is interface static void static function and it's gonna reference t static sub function. Okay, reverse. Interesting. The example implementation. Okay, not that but not in particular that function based derived implementation Though declared before existence of struct derived is known by compiler, that is before derived is declared, is not actually instantiated by compiler until it is actually called by some later code which occurs after declaration of derived. Not shown in the above example. Mhm. So that at the time the function implementation is instantiated, the declaration of derived is not. Technique achieves a similar effect to use of virtual functions without the cost and some flexibility of dynamic parallel. In particular, this particular use of CRTP has been called simulated dynamic binding by some. This pattern is used extensively in Windows. Okay. To elaborate on a example, consider a base class with no virtual functions. Okay. Whenever a base class calls another member function, it always calls its own base class functions. Another member function, it will always call its own base class functions. When we derive a class from base class, we inherit all member variables and member functions that weren't overridden. Okay, yeah. No constructors or destructors. If the derived class calls an inherited function, okay, which then calls another member function, that function will never call any derived or overridden member functions in the derived class. Yeah. However, if base class member function use CRTP for all member function calls, the overridden functions in derived class will be selected at compile time. This effectively emulates virtual function call system at compile time without the cost in size or function call overhead. And the advantage of not being able to make this choice at runtime. Okay. The main purpose of object counter is to retrieve statistics of object creation destruction for a derived class. This is easily solved using CRTP. Let's see. We have static inlet templated struct of counter, and we have objects created and objects live. When you call count, when you call constructor, you get create alive. When you call constructor with the pass by reference, or then yeah, I do the same. Upon destruction